Physics 701. This is chapter 5B lecture. All right, and this is on gravity and Newton's laws. Okay. All right, we've already had the concept of motion in circles, so we have centripetal acceleration is v squared over r. All right, we did that from last. Where v is the speed, r is the radius, so we have going in a circle with some speed. It will, of radius r, it will have this centripetal acceleration. Again, this is related linear. We have acceleration, Newton's second law of motion, F equals ma. Here we have same thing. The force, centripetal force is mv squared over r. All right, so the acceleration makes no difference on the mass. That only depends on the speed, and the radius it is from the outside. Okay. So what we're going to do here now is talk about the last section, and this will be gravity near the Earth's, on Earth's surface, and then gravity away from planet, and orbital motion. All right, so near the Earth's surface, all right, acceleration is g, which is minus 9.8 meters per second squared, and it's roughly linear. So at the Earth's surface, the force of gravity is pulling down, and our weight is mg, and we measure that in newtons. All right, so we've had that before. So near the Earth's surface is relatively constant. Well, this is not actually the case. It actually changes based on how far we are away from the Earth's center of the Earth. So, all right. So what we have here is law developed by Isaac Newton, because we tried to do is analyze the motion of the moon. So we have the moon, right? Motion of the moon, which takes 29 and a half days to orbit. And for him, it was the falling apple. So when the apple fell to the ground, he said he saw the moon at the same time, and he was wondering, is there a connection between these two? Because we know the moon orbits the Earth. So is there a connection? Are they just totally separate things? And he realized they are totally connected. And so Newton came up with the laws in the 1660s. Not going to get into details of that. And from there he developed what we call the law of gravity. And what this is the force force of gravity is given by this constant g, which g is equal to 6.67 times 10 to the minus 11. So it's a very small number. There's a constant that goes with it. So g, big G, times the mass of one object times the mass of the other object, and the distance between, where r is distance between centers. So what you have is, if you have two masses, M1, M2, and 1, and there's a distance r between the center of the masses, this is the force of gravity. Now, it's a very small number. It's a very small force for the most part. And we'll see. Let's just do two quick examples. if we have, say M1 is 1 kilogram, let's say the object between two people, right? One's 100 kilograms, the other's 100 kilograms. And say they are 1 meter apart, all right? Then the force of gravity between them will be given by R will be this constant G, which is 6.67 times 10 to the minus 11th times 100 times 100 over 1, which, you look at this is 6.67 times 10 to the minus 7th newtons. Now keep in mind, 1 pound is approximately 5 newtons. So this is roughly 10 to the minus 7th pounds. All right, that is an incredibly small number. That is 1/10,000,000th of a pound. All right. Oh, I can't imagine how small it'd be. If I had just tiniest piece of paper, which I doubt it can even do, just a little speck of dust would be the amount of force between two people. So the force of gravity is actually very small for the most part, right? This is explained, we'll see later on, this is why, the concept of astrology and planets, and they have absolutely no effect on us. But if you have a very massive object, yeah, it can have a crack. And the fact that gravity is always positive, so it's a very small number. So the force of gravity between two people is extremely small. All right, let's look at then on Earth. Okay? So, on Earth, what it is this is the radius. So somebody on Earth, this is R. R in this case is 6.4, 6,400 kilometers, which is approximately 6.4 times 10 to the 6th meters. Very large number, all right? So the force of gravity between us and Earth is based on how far we are from the center of the Earth. So if you are standing on Earth's surface, and Earth has a mass, radius Earth, mass Earth is 6, roughly 6 times 10 to the 24th kilograms. Then the force of gravity is G, M-E, M, whatever you are, over R sub E squared. And then the acceleration, if we neglect U, this is the acceleration of gravity. Plug in the numbers. 6.67 times 10 to the minus 11th times 6 times 10 to the 24th over 6.4 times 10 to the 6th squared, and we end up with G, 9.8 meters per second squared. So that is what our little g is how far we are standing on Earth's surface with the mass of the Earth and the distance we are from the center of the Earth. This is where g comes from. So it depends on the radius of the object, it depends on the mass of the object. While we're on it, I can talk about, so if we're on the moon, right, the moon is much smaller, has a much smaller mass. So for there, G on the moon turns out to be roughly 1.66 meters per second squared, which is roughly 1/6 g on Earth. So on the moon, if you stand on the moon, it's roughly 1/6. So it depends on that, right? So that's Newton's law of gravity, which is the expression we have. Now, one thing related to this is we get into the concept of the space station. All right, so let's have this. All right, so on Earth's surface, so G is 9.8 meters per second squared, where R sub E is 6.4 times 10 to the 6th meters, all right? Now, so that's on the Earth's surface. Now, if we're on the space station, which is roughly orbiting at, say, 300 kilometers or so, all right? Now, they say, well, you're in weightless. You know, gravity, there's no gravity at that point when you're in free fall. Well, that's not really the case. You're not weightless. What's happening is you are in orbit, and the Earth is constantly falling beneath you. If you were to just have the space station straight up and just straight overhead, it would just fall straight back down. Because let's look at gravity at this distance, right? We have, again, Newton's law. Gravity is Gme over r squared. So if we're this far up, I mean for here, this is 6.4. For the space station, so GSS would be GR would be 6.4 plus 0.43 times 10 to the 6th. And the ratio of this is, and so if we square this, all right, then G of the space station is roughly, that's going to be 0.05 squared, 0.95, yeah. G on the space station is roughly 9 meters per second squared. So it's barely any distance less, barely smaller at all. So how is it that we feel free fall? What happens is we go back to centripetal motion, right? We have, like for the friction, we had the car surface, the friction of the road was pulling us in. Centripetal force is trying to pull us out. Here we have the force of gravity pulling down. And we have the centripetal force, which is mv squared over r, where r is the center. And when these areas are in balance, then you are in orbit. I mean, Newton figured this out. He thought, what happens if I shoot a cannonball to the right and give it some speed? All right, it'll go a little bit and fall down. What if I shoot a little bit faster? It'll go farther and fall down. What if I shoot it really fast? Well, if it goes almost, it falls down. But now if you give it just the right speed, it'll come back, and the Earth is always just falling underneath it. So this is orbit. And because of this, and because we're so far away, this speed of orbit at 300 kilometers is roughly 17,000 miles per hour, right? So it's very fast. So things in orbit are going 17,000 miles per hour to stay there. And that's the law of gravity. And because of this, and we're not going to get into detail, because of the distance, you can figure out the time it takes. So if the speed is 17,000 miles per hour, and the distance, so travels there, distance x is 2 pi r, then the time it takes, or velocity is distance over time, the time it takes would be the distance over the speed. So it'll be this distance, 2 pi r over that, which gives you roughly 88 minutes. So a space station or anything in this orbit orbits roughly every 88 minutes. This is what we call low Earth orbit. Right? So if you're just above the Earth's surface, which is roughly that compared to the radius of the Earth, it takes about 88 minutes. We're not going to get into details of all this. You calculate this. To calculate it more detailed would take more time. And that's not really how we're trying to do. So low Earth orbit, it's about 88 minutes. Now, what if we're farther up? What about the moon? All right? We'll get into 3 different things here. So we have period and radius, distance okay. So for low Earth, I mean, it's roughly our 6 times 10 to the 4th, 6 times 6, okay, and the period is roughly 88 minutes. All right, if we're at the moon, then that's roughly 400,000 kilometers, 250,000 miles. At the moon, then the period is 29.5 days. Right? Because again, the period, the force of gravity goes as G, M, or the acceleration of gravity is G, M, E over R squared, and the speed depends on, and that'll be balanced by V squared over R. So it takes, so you go farther away, gravity falls on, so it's take longer. Now one thing we have is, you ever notice your satellite dish, we have a dish, satellite or any kind of satellite, they point at one spot south. Right, they don't move around. I mean, you see the space station, it goes around pretty quickly, every 90 minutes or so. But if we look at satellite, what we call a geosynchronous, then what it does, it stays in one spot 24 hours a day. It stays in one spot. This is what we call a geosynchronous satellite. And in this case, that's a period of 24 hours. And the way that works is it's approximately 42,000 approximately 42,000 kilometers above Earth. So they are about 25,000. So they are, it orbits 24 hours, with a period of 24 hours because it's at this point. So these are the three things. You're close to Earth's surface, it's 88 minutes. You get up to geosynchronous, 24 hours. And at the moon, it's 29 after. So, and this concept of low Earth orbit also deals with planetary motion. So in planets, so here we'll leave this up. I'll talk a little bit about planets and leave it there. I'm not going to get into details to be conceptual. All right. So, to talk about the planets, and this has to do with Kepler's laws by Johannes Kepler around 1630. All right, you have the sun at the center, Mercury, Venus, Earth, Mars, blah, 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 all the way out to, say, Pluto, which, people don't want to call a planet, but what the heck. All right, they're farther out away, and so Earth is what we call 1 astronomical unit, which is about 150 million kilometers, has a period of 1 year. Mercury, on the other hand, is very close, has a period of only 88 days. All right? And then Pluto, at the far extreme, has a period of 248 years. So you get things way out there, and then there are things that are actually beyond that, and they have periods of thousands of years. We get the comets. All right, we're not going to get into that kind of thing, orbits and things like that. It's not an astronomy class. You have comets that have periods of up to 30,000 years. All right, they are so far out there, they take forever to orbit. So this is all related to Newton's law of gravity of little m over r squared. So this is the summation of chapter 4. Okay? Chapter 5, I should say. So on later this week, I'll do the review for exam 2 on chapters 3, parts of chapters 3, 4, and 5. So have a good day, and